Okay. So it's our Thanksgiving week data mining. It's really close to the end of the semester. We only have five class sessions left. And so I wanted to start us off with a highlight of what to expect from the rest of the semester here. So the biggest thing coming up is after Thanksgiving, the following weekend will be the next and last midterm for this class. And so again, it'll be the same sort of schedule like we've had for the other ones, that you'll have the whole weekend to complete it, starting on Thursday and going to Sunday. We will not today finish up all the material for that, but probably on Monday finish up all the material for that. And again, happy to have a review session for that that week if people would like. There's going to be two more programming assignments in this class. Today we're going to talk about this Vowpal Wabbit program and how to use that and how it relates to everything that we've been talking about. The due date for that is basically just before the midterm up here. That I want you to have as much time to work on it as possible without there being any overlap with the midterm. It's a little bit tight schedule-wise. I apologize that we had to cancel the last class last week, but hopefully that gives everybody enough time. I don't think it'll be a too time-consuming problem. And my also hope is that you don't have to work on it over Thanksgiving break, that you can either finish it tonight, tomorrow, or early next week and not have to work on it over Thanksgiving. There'll be another assignment that you work on between the midterm and the final exam, and then we'll have the final exam during finals week. Both of these assignments up here will have pretty good extra credit opportunities, and we'll again be talking about the Vowpal Wabbit one starting today, and then the Word to Vec one later. And for the final, mentioned this sort of in passing, but you'll be the final exam, again, totally oral exam. Everybody will be meeting with me one-on-one to talk about things in the class. And again, the last week of class before the final, we'll talk about the exact format of that and how to prepare. But you can go ahead and schedule your time slot if you'd like on this Google Sheet. And if you do that, it just takes you to something that looks like this, and just type in your name anywhere in one of these boxes, wherever you want to have your final exam. And if for whatever reason none of these time slots work for you, send me an email and we'll work out something that does work for you. Any questions on anything administrative related to any of those, timeline, what to expect? Yes.
Is there going to be a question sheet or anything for the final?
Yeah, so exactly how the final will work. We'll talk about the details of that the last week of class, but basically it's going to be, I'm going to randomly select questions as soon as you enter the office from the previous midterms, and you'll just answer those questions, explaining to me like what your reasoning is. Both from and similar to, yeah. Yeah, we'll have a whole week to talk about the details. Good question. Sorry, it's not a totally fulfilling answer maybe at this point. But any other questions, timeline-wise, things to expect? Okay. Last class session, we were talking about the last thing in the book, this chapter 4.3, validation. We didn't finish this yet. We're at a decent pausing point though, so we're not going to finish this today. I want us to make make sure that we have enough time to talk about all the Vowpal Wabbit stuff. Very hard to say. And then we'll probably finish this up on Monday. So we'll pause the validation and work on Vowpal Wabbit here. If you come over on our class webpage, there's a new folder, 08 applications, Vowpal Wabbit. And under there is both the notes for today, this notes.pdf, and there is this README file explaining what your next homework assignment is. And so we're going to go over this README file about what Vowpal Wabbit is, how to use it, and this assignment today. High level, Vowpal Wabbit is an extremely fast machine learning system maintained by this guy, John Langford. John Langford, so he's working at Microsoft Research right now. He's extremely famous in the machine learning world. He previously was working at Yahoo Research. That's actually where he started this Vowpal Wabbit project. But then Yahoo went bankrupt, and all the other FANG sort of companies had like a fire sale trying to hire all of Yahoo's machine learning people. And Microsoft Research, they didn't previously have a branch in New York City, but they basically created the branch in New York City just because they wanted to hire this guy and he didn't want to leave New York. So now he's working at Microsoft. It's widely used in industry. So real quick, my guess is that probably has anybody here heard of Vowpal Wabbit before? Yeah, it's not nearly as famous as things like PyTorch, TensorFlow, scikit-learn, but it's in terms of like the number of dollars that it's generating for companies, it's probably the most profitable machine learning library out there. If you follow this link, it takes you to this wiki. These top one links right here, these are companies just that John Langford's somehow been directly affiliated with. So Yahoo, spam filtering, eHarmony, if anybody has or will use that, all the decisions at eHarmony being made by Vowpal Wabbit. And it's used also all over the place internally at Microsoft. One of the, coming back over here, oh, not there, here, the program itself is state of the art for like what I would consider to be simple text-based problems. So examples of simple things are if you're on a web page determining which ads to display to a user. Every ad company that I know of like where I know their internals is using Vowpal Wabbit internally to display their ads. And so that's why I say it's probably the most profitable like library, because ads are like the most profitable thing out there. Things like deep learning, not at all suitable to ads. If you're on like the New York Times webpage, whatever articles they're actually displaying to you based on your previous browsing history, that's done with Vowpal Wabbit. And similarly, social media web pages, whatever like goes into your feed, that's all done on many platforms done with Vowpal Wabbit. And we're going to be, for this particular assignment, what we'll be working on is you're going to create a machine learning model that's going to determine political bias of a piece of text. So whether that text is pro-Democrat or pro-Republican. And so that's, again, one of these things that I would consider to be a relatively simple text-based problem. In order to get good results on that, you're going to have to use all of the VC theory stuff that we've been talking about the past couple months in class. And so this assignment's going to get you a chance to practice all of that and see how all that applies to a real world problem in decision making. A couple of fun notes here. So complex text problems, again, probably requiring deep learning, but most actual like business problems are not these complex problems. And in general, when people set out to solve one of their problems, they'll probably start off with Vowpal Wabbit and then only switch to another system when something like deep learning, PyTorch, when Vowpal Wabbit's not getting good enough performance. Again, extremely famous among machine learning professionals. and much more valuable in practice, I think, than like PyTorch TensorFlow. We're going to be using Vowpal Wabbit's command line interface for this assignment. It does have a Python interface that's compatible with scikit-learn, but I don't know anybody who uses that because it's much more awkward to use. If you're not super familiar with the command line, it might feel more awkward at first, but this is far, far more simpler than writing Python code to do all the stuff we're doing. So this assignment will have to be done on the Lambda server, and I know a lot of people don't have a whole lot of experience working on these remote machines, and so I'll do a little bit more background of that today. But it will have to be done on the Lambda server because that's where the data is. The last thing, quick fun aside, it's open source and it actually has contributions from North Koreans in the source code. So you'll be running North Korean software on your computer or on the Lambda server. Any questions at a high level about Vowpal Wabbit before we get into details?
If the clone repo is the data folder already on?
Data folder's already on there. And we'll be seeing that here in a second.
Do you have to port for anything, or is it like all command lines?
Everything's command line. All the things that I want to say all the things that real people actually use, where real people means like people working in production, is 100% command line stuff without visualizing anything. And so, and yeah, same here. So the data set that we're working with. Again, we're trying to, given a piece of text, determine whether it is pro-Democrat or pro-Republican. And one of the difficulties of any problem like this is just gathering the data. And something like this, maybe the most obvious way to label some data like this would be to hire some people, or for you to do it yourself and just manually label, sit down, read these texts and decide, oh, this is obviously Democrat or this is obviously Republican. But this has three relatively obvious problems, relatively major problems. The first one is that it would be expensive to generate labels, and either expensive in terms of your own time sitting down and doing that, or expensive in terms of actually hiring other people to do that. For a problem like this, we're going to see that our data set has about 200,000 tweets inside of it, and hiring people to label 200,000 tweets would take a long time, be super expensive. Furthermore, those labelers may not agree about like what texts are pro-Democrat or pro-Republican. There's going to be a lot of edge cases, and won't be obvious. And then we would still have to decide like which texts we want to have the labelers label, and that'll have a big impact on our actual results. So one of the, I don't know, tricks that data mining people do is we somehow find like labels or text things in the real world that are naturally labeled somehow. And what we're going to do in this case is we're going to look at a data set of congressional tweets. So here's the repo. It's already been cloned onto the Lambda server. I'll show you how to access it here in a second. But this repo has every tweet sent by every member of Congress since 2017, middle of the year, up to yesterday. And our basic assumption is that if it was a Democrat who sent the tweet, then it is pro-Democrat. And if it's a Republican who sent it, then it will be pro-Republican. And so by using this transformation, we will not have to manually label these things and get those labels for us automatically. The data set itself is, you can find one of the files located right here. And I've already pre-processed the data, put it into a format suitable to Vowpal Wabbit. So you don't have to worry about any of that pre-processing stuff. You'll be able to focus just on the all the hyperparameters, like which hypothesis class to select and things like that. I'm going to come over to a terminal window here for a second. And there we go. Here I'm just logged into the Lambda server on my account. And this is the location of what's going to be our training data. And I'm going to use this head command to output the first 10 lines of this data set. Each one of these lines, the format of this line is that there's a vertical bar right here, the pipe symbol. The thing to the left of the pipe symbol is the class label, -1 and +1. -1 will be Republicans, +1 will be Democrats. And then to the right over here is the text of the actual tweet. And the pre-processing that I've done is I've removed all the grammar features like periods, commas, URLs. If there's a hashtag, I just removed the hash in front of it. Or if there's a mention of somebody, the @ symbol, I removed the @. But all the words are still there. And so this text message right here talking about Marco Rubio, this tweet talking about Marco Rubio. So it's going to be a Republican one, and this one down here talking about Planned Parenthood, going to be a Democrat tweet right here. If we want to see the total number of tweets in this data set, the command to do that, wc-l, gives us the total number of lines in a particular file. And so this file right here has 134,000 lines in it. So Congress has sent 134,000 tweets. And if we look at, this is going to be our training set, everything sent up until 2021. If we look at the data set in 2022, then there's another 20,000 tweets in our training set that we'll be working with. And that's all that this next information here is talking about. You're not going to need to know the details of that training format in order to work with Vowpal Wabbit. It's going to process all that for you. But does anybody have questions about that? Okay. So then the assignment itself divided up into 2 tasks here. This preliminary task is just to make sure that you have sort of a sane working environment that you can successfully run Vowpal Wabbit and do the things that you need to do. And then the second task is going to be to actually configure things about your hypothesis class and training procedure to get the good results. So this command right here is going to actually run a train the model using Vowpal Wabbit. So the VW command, short for Vowpal Wabbit. Anytime I have one of these $ commands right here, you take whatever is to the right of the $ and you copy and paste that into your terminal window. So let's reset, clear that off. And I'll paste this right here. And as soon as I did that, so here's the command that I pasted right there. This is what the output of that command is going to look like. And the main, let's see, let me come back over here for a second. So breakdown of what this command is, this VW right here. So for Vowpal Wabbit, this -d is the data set that you're working with. This is going to stay the same for everything that you're doing. So you can just copy and paste this. It's always going to be this file right here that you'll work with. This -f is the trained model, what you create, where you're saving it to, the file name that you're saving your trained model to. And so as you're working, you'll probably want to create multiple different models to compare them. And you'll want to change this model.vowpal wabbit to different file names in order to have multiple models that you're working with at once. This loss function is logistic, and this -- binary, also things that are going to stay the same for all of your runs, just telling it to actually do logistic regression and report the 0-1 loss in the output. The final output is pretty big. So this whole output that I have listed right here is the same as this output that we got over here. And the important features here that you need to look at, that these are the sort of intermediate debugging steps as it's training. We'll talk more in detail about the training procedure in a little bit. And then this line down here, this average loss line, this line right here is going to be the actual, like, in this case, it's a validation set loss right here. 0.05 is the validation training accuracy. And this is the 0-1 loss right here. Yeah, we'll talk more about interpreting all of these results here in a second when we talk about the internals of what Vowpal Wabbit's doing. But yeah, question. Question is it being recorded? And yes, the whole lecture is being recorded. It'll be up on YouTube, so you'll be able to, if you're missing something, go back and get it later. Follow along with those commands.
So we should touch like using logistic progression and like in the binary.
Question is, here we go. Should we touch these things? And the answer is that you can. It's guaranteed to give you worse results though, so you don't want to. The only thing on this line right here that you'll want to change is this number 3, this -f, changing the name of the file that it's outputting. And then we'll be seeing other hyperparameters, other options that you can be adding to this command in order to change the particular hypothesis class that it's creating. But these two and these two should stay the same for everything. Good questions. Any other questions so far? Question is, where does the name come from? It's from Looney Tunes and Elmer Fudd and how he pronounces rabbit. And John Langford just liked Looney Tunes. Yeah. Okay, so this actually trains a basic model for us. And I'm going to come back over to the terminal right here. If I type ls right here, you can see that, so again, ls lists the contents of my current folder. There is one file in here, this model.vw file. rm will delete a file, so rm model.vw, ls, there's nothing in this folder anymore. And I'm using the up arrow right here to go back to the previous commands that I've run. I'm going to rerun this Vowpal Wabbit command like this and type ls, and here's my trained model right here. And again, notice that this Vowpal Wabbit training happened super fast. It was about a second or two to train on this many tweets, 134,000. Vowpal Wabbit's regularly used on like terabytes of data in size. It's by far the fastest machine learning system that people use regularly. So you should, if things are taking a long time for your Vowpal Wabbit to run, then something's probably going wrong. Everything should happen really fast. But every time you run this again, this model.vw here will be created. And if I rerun this again, so rerunning the same command like this, it's not going to give me an error message about the model.vw already existing. It's just going to overwrite it and delete whatever you had previously. In order to use this model, this next command down here shows us how to take a particular string and ask, is it a Democratic string or Republican string? There's a whole bunch of stuff up here. None of that, well, the details here down are down here. The -i tells us which model to load. The I stands for input. The -f when you're saving, the -f stands for file, -i for input. So which one are we inputting? The -p here stands for predictions. So where do we want to print our predictions? /dev/standard out means print it to the screen so we can visually see it. Again, the -binary will give us the 0-1 loss, whether we think it's a Democrat or a Republican, +1 or -1. --quiet means that it's only going to print this and not a bunch of debugging information. This here is called input redirection, and it takes whatever is in the following string and passes it to your Vowpal Wabbit program. So here I have a string about the Affordable Care Act, and if we pass that to our model using that command right there, then it'll give us a 1 here because things about the Affordable Care Act, that's a Democratic Party act. And so it's giving us a 1 right here, that the Democrats are talking about that a lot more than the Republicans. Similarly, down here, I have a Republican-oriented tweet. And if we copy and paste that down here, then we get the -1 because it's a Republican tweet. Apparently, this Institute of Caribbean Studies, I looked at their webpage. I'd never heard of them before. They talk about being a bipartisan institute, but for whatever reason, only Republicans talk about them in their tweets. So I don't know how bipartisan they actually are. So both of those two tweets, maybe if you think about it a little bit, it seems like we can come up with justifications about why the model's labeling them as Republican or Democrat. But it's more broadly important to interpret our model's overall test accuracy to get the test accuracy. And that's what this command right here is going to do for us. Again, so Vowpal Wabbit, the -D is specifying a data set that we're working on. In this case, we're getting the test accuracy here, so data _ 2022. The -I for the inputting the model, the -T right here says that we're testing the model and not training the model. One of the, I don't know, I'm pretty pro command line, but one of the difficult things about this Vowpal Wabbit command line is like, why should -T be for testing? That training also starts with a T. Why didn't you make your commands a little bit more self-documenting? But -T is what John Langford chose for this. And so -T here does the testing. And again, the -- binary will give us our results in the 0-1 loss instead of the logistic loss. And if we come over here, run that, again, there's going to be a lot of output, but it's this average loss right here that we're going to care about. And so this default parameter model, this default model is giving us like a 9% training error. And that's actually a lot better than I initially expected that a model like this would get. No tuning at all, and we're getting 9% error determining whether somebody's a Republican or Democrat. So pretty good predictions here. Your specific task, though, is going to be to train a model that's going to get less than an 8% error. So reducing the error by 1%. I was able to get it down to 7.5% with a whole bunch of tuning. I think the 8% is very reasonable to get to. So if you get to the 8%, you'll get full credit. But the extra credit on this assignment, and this is 2% added to your final grade in the class. So probably enough to bump you up to the next like partial letter grade. If you can get down to the 7.5% error rate. It doesn't seem like a big difference. And on this task, maybe it's not too big of a difference. I don't know if you really care between an 8 and a 7.5% error rate here. But if you're one of these ad companies managing billions of dollars in ad spend, then a 0.5% performance increase is like a couple $1 million. So that's a huge deal. We're going to talk about next in class is like, what are the other flags that you can pass to this VW program, to Vowpal Wabbit, in order to change the statistical properties of your model here, in order to reduce the test error down to these numbers. But before we do that, are there any questions just about the assignment itself or the use of Vowpal Wabbit in the command line? Okay. Then we will switch over to here, to the notes. And we'll talk about exactly what Vowpal Wabbit's doing internally with all of these commands and how to manipulate it to get it better statistical errors. So the first thing is, and we've talked about this a little bit before. Where's my cursor? Computer's not detecting you. There we go. So one-hot encoding. We talked about this in the context of feature transformations and the VC dimension. But now we're going to talk about it specifically with regard to text. And if we have our input string that looks like something like, we had the tweet that said the Affordable Care Act, and then it had a bunch of other words inside of it. Then in the one-hot encoding, we are assigning each one of these words an individual vector that's going to look something like they'll have a whole bunch of zeros and then a 1 at the location for that particular word. So this here's the location for the, and then maybe affordable is 0, 1, 0, 0, 0, 0, 0. So that's the spot for affordable. And then say that care is all the way at the bottom. And act is 1, 2, 3, 1, 2, 3, like that. And then our final feature vector, the thing that's going to be the input to our model, the X value, is going to be the sum of all these things together, the sum of the feature vector for each individual word. Add all those things together. In this case, we get 0, 1, 1, 0, 1, 0, 1, I believe. Something like that. And this is going to be our X value, our input to our model. Yeah, so this is a great observation. The observation is that here, the location of the word in the sentence actually has no impact on our representation over here. That this sentence right here would give us the exact same X value as the sentence act, care, the affordable. Has the same X value representation. And so that seems like a totally ridiculous thing to do. Like we're throwing away tons of information. But for the vast majority of text classification problems, you actually don't need to know where things occur in the document in order to get good results. That whether somebody is talking about, in our Democrat versus Republican case, if they're talking about the Affordable Care Act, if these 4 spots are indicated as 1, I doubt there's anybody who said the words the Care Affordable Act or the Act Affordable Care, any of those other permutations. People just don't use those combinations. And so this turns out to be a good enough representation for most problems. Great question. So here I have each word only one time. The way Vowpal Wabbit interprets one-hot encoding is that if you have a word multiple times, so if somewhere else we have the word the, it's an orange. If there's another the over here, then there'll be another vector 0, 0, 1, 0, 0, 0, 0. And we'll add that together, and this will be a 2 right here instead of a 1. It turns out that whether you consider duplicates or not consider duplicates, you're basically always going to get the same exact results. And it just happens to be computationally faster to not remove duplicates. And so that's why Vowpal Wabbit doesn't remove duplicates. I'm sure there's a flag that you could pass into Vowpal Wabbit that would make it remove duplicates. It would just be a little bit slower and the results would be the same.
So like this vector is just one time.
Yeah, so here's another great question. What is the size of this vector? It's a very important question for us to get a handle on for our statistical discussion. And so I'll phrase this as, what is D? So D again being the dimension of our vector. Or the equivalently the number of features that we're using. And so what is D? The most naive thing to do is that you make D just be the size of your vocabulary. And so by vocabulary, I mean the number of distinct words that you have in your entire data set. The problem with that, though, is somehow we have to calculate then the number of features in our data set. And it's, in some sense, that's not too difficult to do, but it's still a painful, time-consuming process. Calculate D in advance. One of the reasons that Vowpal Wabbit is so fast is that it only has to look at every data point exactly once. And if we wanted to know the total size of our vocabulary, we'd have to do multiple passes over our data set, looking at the data multiple times. So the Vowpal Wabbit does something called the hashing trick to eliminate this problem and make computation much faster. In the hashing trick, we set D to some fixed size before we even start our learning problem. In Vowpal Wabbit, this size is always a power of 2. And that's for, again, computational efficiency reasons. VW, D is always a power of 2. So something like 2 to the alpha, where alpha is an integer. And then we have a hash function that converts an arbitrary input, and I specifically mean an input string or word, into an integer. And then our one-hot encoding representation is just going to be the index of that hash function for each word. As a vector with the index of the hash equal to 1. It's very similar to the one-hot encoding that we're talking about above, but now we're not doing any pre-processing of the data, not calculating the entire vocabulary in advance. We just have this hash function. And the downside of this is that multiple words are going to get mapped to the same hash value. So in our example above, it might be the case that like hash of the is equal to 5 and hash of affordable is also equal to 5. And so not only can we not tell if the words are in what order the words are in, but we actually can't even tell like what the actual word is. All we know is that it's either the or it's affordable. Yeah, so the question is, will our dimensions here be less than the size of the vocabulary? And exactly, that's the reason why you want to use this, is you can make the dimensions of your model less than the size of the vocabulary. And it turns out that this is actually an example of that random feature map that we talked about before in class. This is an example of the random feature map. That you can interpret the hashing trick as you originally had some larger dimensional space, one for every individual vocabulary word, and then we're hashing it down to some smaller space using a random matrix that's represented by this hash function. And so what we're accomplishing by that, we're making the D smaller, so we're getting better generalization error. But the downside is we're getting these hash collisions. We can no longer distinguish between certain things. And so we're making our training error go up. The training error increases, but the generalization will decrease. And I'll specifically add over here, this is as our D dimension decreases, as D goes down. So if we make our dimension smaller, our training error is going to go up. We'll get more collisions. This is an example of a hash collision right here. But the generalization error also goes down, and so it's a trade-off thing. The optimal D value here that you have to pick will depend on whether your training error or your generalization error is the thing that is too difficult for your problem. I have a I'm going to visit this web page right here in a second, and we'll look at some plots of this trade-off. Before I do that, are there any questions about what the hashing trick's doing? Go ahead.
Can you write like what you have to write on the command line?
Yeah, so the question is, what command line thing manipulates the hashing trick? So manipulates the size of your hash. If you come down here to page 3, this important hyperparameters section, it is this bit precision right here. This controls the size of hash. And in particular, if you set bit precision equal to alpha, then the size of the hash is equal to 2 to the alpha. And so as your alpha value increases, as alpha increases, then your hash table, the size of your hash functions gets larger. So there's fewer collisions, training error will go down. But your dimensions also goes up. That also implies that your features goes up, which implies a larger VC dimension. And so more generalization error. Vowpal Wabbit's also trained with stochastic gradient descent. And we saw that stochastic gradient descent, the runtime is proportional to the dimensions. And so alpha increasing will make the runtime also increase. Not significantly, you're not going to have any problems with runtime on this assignment. But you will notice that if you make the alpha very, very large, it will take longer. Bit precision is the exponent in the hash size. Exactly. So it's bit precision right here because it's the number of bits used in the hash. And so the total size of the hash is 2 to that value. I believe the default value here is 18. For alpha, it's bit precision. If you want to get more details on any of these parameters as you're working with it, there's this web page up here if you want to see it in web page format, or what I personally find more convenient since I'm already in the terminal. I look at the man page for VW, type man VW, and it gives me the contents of that web page just in the terminal right here. And then I can search the man page for whatever option I'm looking for. In this case, it's bit precision. To search, you press the / key on your keyboard, /, and then search for whatever word you're looking for. Bit precision right here, the number of bits in the feature table. So the explanation about this one's not particularly detailed, I guess, because it's so fundamental that they wouldn't be able to have a fully detailed explanation. Good questions. Any other questions about this bit precision before I go to the plots?
Show us how to change one of these parameters?
Sure, yeah, great question. So the question is how to actually set this in practice. If we come over here to the terminal, I'm going to press the up arrow button until I get back to my Vowpal Wabbit training command. Actually, instead of doing the up arrow, I'm just going to come back over here to the instructions and find the spot where I trained the model. That's this one right here. It says train a simple model. And I'm just going to copy and paste this command back into the terminal for a second. Copy that, come back, here's the terminal, paste that here. So this is that same command. And then in order to actually specify one of these hyperparameters, I'll do -- bit precision right here. Bit precision, and we'll say that that's equal to, let's try 22 instead of 18. And it'll run that, still very fast. You can see now that my average loss right here is smaller than it was before. So let's just remember this number right here, 0.0725, up arrow, change this to 18. So by making my bit precision smaller, I'm expecting that my training error is going to increase because I'm having more collisions on this hashing function, but my generalization error will decrease. So again, here, this average loss is It's on our training set, so we're going to expect this value to go up by making the bit precision go down. I hit enter, and now the average loss a little bit higher, I think, than it was before. 74, 72. So that's, yeah, any one of these parameters that's controlling something about your model. This is how you add it to the command line to specify what that is. The order of these things doesn't matter at all. All that matters is what the value is. But here, another good practice is anytime I add a new hyperparameter, changing my model over here to somehow reflect, this is the name of the file that I'm saving, to reflect that this is a new model trained with different parameters. So I'll say dash bit precision equals 18 right here. So this is my new file name. One trained on 18. Change that one to 22. Change this one to 22. And now if I type ls listing all the models, I can see how I have this one right here where I don't know what the hyperparameters were because it's not in the file name at all. But these ones I can clearly see what the hyperparameters are. And so if I want to evaluate them, I know what the hyperparameter was in order to keep that value. Does that answer your question? Yeah. Question, no?
So like the way the hash is populated by the training plan?
What do you mean by the hash is populated?
The way it like assigns hash values to each word.
Great question. The question is, so here I just made up two hash values, hash of the is equal to 5 and hash of affordable is equal to 5. How exactly does Vowpal Wabbit assign a number to the individual words through this hash function? This is not something that is learned from the data set at all. This is something that is just like hard-coded in, there's a bunch of great hash functions that I would guess it would be a cryptography class that you would normally talk about hash functions in detail, but that convert strings into basically essentially random numbers, and there's no way to predict based on what the string is what the number will be. And if you change this string even very slightly, the number over here is going to be arbitrarily different. So the right way to think about it is that this is just a random number, but you're always going to get the same random number for each string. Okay, coming over to this link. Copy that in Firefox. Control V. So this company, booking.com, they, I believe it's plane flights that they focus on booking, but they're talking about how they use Vowpal Wabbit internally in order to do their various predictions. And they have an explanation of the hashing trick up here in detail if you want a different explanation of that. And then they have a bunch of graphs down here about how the hashing trick actually works in practice. And over here on the right-hand side, this is a measure of the training error. And then on the left-hand side over here, this is a measure of the hash size. So this N right here is what we've been calling D throughout the class, the number of feature dimensions that we have. And it's a plot of how many collisions you get as the hash size changes. And you can see that surprisingly, as the hash size decreases, the number of collisions stays very, very small until the hash size is really quite small. So 10 to the 20th is 1 million different words, and 10 to the 16th is like, I don't know, 200,000-ish. And it's only about at that point where you start getting the number of collisions actually significantly impacting your log loss. They verify this on a bunch of other data sets as well. And even when you're getting like way over here on the right-hand side, lots of collisions, it still doesn't have an impact on your log loss, on your training error for a long period of time, just because most words are not meaningful for your particular problem. If on our problem, like Republicans versus Democrats, the only way this is really going to be a problem is that if somehow a word like affordable, something that's probably likely a key Democrat indicator, gets mapped to another word like, I don't know, voting fraud, that is a key Republican indicator. But as long as it's just mapped to a random word, then it's not going to have a bad impact. Let's go through some of these other hyperparameters down here. These first sets of hyperparameters are about the hypothesis class, the VC dimension. I recommend tuning these ones before turning the second set of hyperparameters down here, which is about the optimization. And then once you're satisfied with your hypothesis class, then go on to the second set. This bit precision is by far the most important one. This hash seed, you can specify a particular number, and it's going to just change what the random numbers changes the random numbers assigned by your hash function. There's no impact on D. The number of dimensions you have. So no impact. No impact on generalization error. But it's always possible that you just get a really bad random function that assigns every Democrat word to an equivalent Republican word. And so changing the seed can potentially change your training error. Potentially change training error by reducing the number of collisions. For reasonably large data sets like ours, this is not likely to be a problem. So unlikely that you'll have to change hash seed, very likely that you'll have to change bit precision. Quadratic here means apply the quadratic feature map. In this case, the quadratic feature map gets applied before applying the hashing trick. So this means that hash function gets applied to word pairs instead of individual words. And so it might be the case that like affordable care, those two words, they have to be together in order for it to be a democratic indicator. And if you just have the word affordable or just have the word care, then it's not a good democratic indicator. And the quadratic feature map would be able to identify that for you. Because this happens before the random projection, it will have no impact on D. And so no impact on the generalization error, only impacts the training error. And then this cubic one is same as quadratic, but for the cubic feature map. for very large scale problems, it turns out that larger degree polynomials almost never useful in practice. And so cubic is the largest polynomial that Vowpal Wabbit implements. Any questions about those? No?
Can you explain how quadratic just affects
Yeah, that's a great question. So normally when we've been using the quadratic feature map on a linear classifier, we have had just a single feature map being applied. Here, though, we have two feature maps being applied, that we have this V2, call that the quadratic, and then this, goes from roughly D into D squared. Both of those are in asymptotic notation. But then we also have our random projection, I'll call it phi b, is the random projection. And in this case, this will go from the D squared down to the D prime, the new feature map that we're going to, this D prime being what I called before, to the alpha. And we're composing this by, you first do the quadratic feature map. You first do that on D, and then you take the output of that and apply the random projection onto that. So it does change the dimensions on the in between here, but the thing that our model actually sees is the output of the random projections, and so that stays as a constant. So the generalization error will stay the same. It's only going to potentially affect the training error. The question is, what's the point of the quadratic? The answer is that it affects the training error. So if we keep the generalization constant but can lower the training error, then we'll get better results. So the intuition about when you would want to use the quadratic is that if we have two words in our tweet and we need both of those words in our class to indicate the class label. So maybe this word care right here, maybe the Republicans are talking a lot about veteran care. And so the word care by itself is not indicative of it being a Republican or a Democrat tweet. In order to know whether it's Republican or Democrat, you have to know, are they talking about affordable care, in which case it's the Democratic tweet, or are they talking about veteran care, in which case it's the Republican tweet. Yeah, so it's still ends up being a little bit trial and error-y here. But yeah, this will potentially decrease your training error, not going to affect your generalization error because it's happening before the random projection. The neural network right here, dash NN, this uses a neural network instead of a linear classifier. And so there's a number that you have to pass in right here about the number of hidden layers that you want, but this can potentially make your training error go way down, but the generalization error way up. The n-grams is like the quadratic. So the neural network is the sort of the general feature learner. We don't know which feature thing to use. So the neural network says, let's learn the features for us automatically. The n-grams here is a text-specific feature generation method. If we have n-grams equal to 2, so 2 grams, then when we have the Affordable Care Act, we'll get the features for the affordable will be, this is a 2 gram right here, these two things taken together at the same time. Care, affordable comma care. And care comma act. We'll get these features right here. What we will not get is anything where there is spaces between the words. So we will not get things like the comma care or the comma act. These ones in red over here, the quadratic kernel would get these. So if the n-grams is working better than the quadratic kernel, it means that the only thing that matters are pairs of words when they're right next to each other. But the quadratic kernel considers all pairs of words. And so if that's working better than n-grams, then it means that we care not just about the neighbors of words, but if 2 words appear anywhere in the tweet together, then they're important. This is going to have the same properties as the same properties. It's supposed to say properties as quadratic kernel, but it's less severe because it's not considering all the combinations, but it is a bit less severe, and it's a little bit more tuned towards text applications. This number right here as well can be as high as you want. You're not limited to 2 or 3. It can be as large as you want. And if you make that number large enough, then you're guaranteed to get your training error to go to 0. Question, Kieran?
So then you wouldn't use both the quadratic kernel and the n-grams kernel, because n-grams kernel like a subset of quadratic.
Yeah, the right way to think about it is that the n-grams is a subset of quadratic. Good observation. Okay. The skips right here, I'm going to skip over this one and let you read the documentation about those ones and move on to these L1 and L2 since they're more important. These are the regularization hyperparameters. And it's in particular the lambda version, not the C version. Good values to select from for these lambdas. You want to do things in the range of like 10 to say the negative 15 to 10 to the 5. I've never seen something outside of that range before. And when you're considering these different values, then you want to do it like with exponential step sizes. So trying like 10 to the negative 15, 10 to the negative 14, and so on to 10 to the 4th, 10 to the 5th. And we've previously talked about how these things affect your hypothesis class. And so which ones, depending on your generalization error, training error needs, what direction to adjust those in. L1, again, induces sparsity. Induces sparsity. And text problems sparsity is often good for text problems. I would first, in the order of doing things, get the hypothesis class fixed using the this bit precision. Then I would work on my these other feature transformations right here. Depending on how these feature transformations go, you might need to adjust your bit precision. Increasing the bit precision at the same time as increasing one of these values will have a counterbalancing effect. And then once you have those determined, then select your regularization right here, and then move on to these optimization parameters down here. The main thing that I want to say about these optimization parameters is that the only thing they will affect is your optimization error. And so once you've gotten your hypothesis class as good as you can, changing in particular these passes or the learning rate down here is likely to give you just a last little bit of boost in performance. And yeah, the other ones will be less important. I think that's a good stopping point for us today. That's enough that you can get started on the assignments, and hopefully shouldn't take too long to finish it. Again, just basically working from the top down on these hyperparameters, getting them adjusted in order. You should be able to get the result that way. And that's it for today. You're welcome.